Good afternoon, class, or morning, depending on where you're at. So now we're going into week 11, and I hope everybody's been safe and healthy thus far. I am still in the process of getting everybody's samples prepared for your in-lab sessions. But to start off this week, we're going to be talking about some practical interpretation of aluminum alloys, differences between cast, wrought, and different etching techniques, and some of the micro constituents that you would uh, run across. So kind of an outline, just an intro to aluminum, because it is important and it is used in our daily lives. So some info and properties, go over some temper designations. It's always important to talk about the heat treatment and or uh, strain hardening condition it's in when identifying your aluminum alloys. So cast, wrought, and once again, just to understand and use common language, that'll give you the ability to describe those structures. So what is aluminum? Well, behind iron, it's the second most plentiful metal on Earth's crust. It is a reactive metal. In 1889, sufficient enough aluminum was then being able to be produced for engineering purposes. Um, and of course, recycling aluminum saves a ton of energy and a ton of water, and it does not deteriorate when you recycle it. So what are some of the properties that you can expect out of aluminum, and why we use it in case iron is or steel is not available? It's typically because of its strength to weight ratio. You have good corrosion resistance. It's a good electrical and thermal conductor. The formability, it's non-toxic, it's heat reflective and light reflective, and it has no low temperature embrittlements. So pure aluminum in its purest form is pretty weak. It's only at 1.5 KSI, but you can alloy it in order to come up with strengths approaching 100,000 KSI, or I'm sorry, 100,000 PSI, 100 KSI. And just like steel and ferrous alloys, there are ways that you can strengthen your material. For aluminum, it's a little bit different in the sense that you will solid solution, so you solutionize your aluminum alloy, and then you have the ability to then cold work it. The next one would be to precipitation harden. It's a precipitation treatment. So what are some of these temper designations that we'll be talking about? So when you're looking at aluminum, if somebody tells you, you have a 6061 F aluminum alloy, then that is designated as an as fabricated condition, whether it was cold worked, hot worked, cast, etc. The moment that material is in its final form, that is as fabricated. If you take that as fabricated component and now you anneal it, now you're softening it, so that would be the condition that it would be in its lowest strength. Strain hardening is identified as the letter H, and there are various numbers after all of these, but H would be for strain hardened, and that's for wrought alloyed products only. You will not strain harden a casting. Then you have your T designation. Typically, your T designation is your precipitation hardened condition. So it has gone through a heat treatment. Okay, whether it's naturally aged, artificially aged, or cold worked, then aged. Those are some of the differences in the designations that you'll see. The very most common aluminum alloy is a 6061 T6 alloy. So cast and foundry alloys, just like everything else, your properties are going to depend on the grain size. And for castings, it's going to be the shape or the dendrite arm spacing. Also, the size and shape of your secondary phase particles are going to have an impact on your properties as well. So with increasing cool rates, you reduce the grain size and also reduce the dendritic arm spacing. And just like with iron or ferrous alloys, there are elements that can be added to modify either the dendritic spacing, the secondary, the shapes or morphologies of the secondary phase particles. And for aluminum, it's typically sodium, strontium, and silicon. So taking a look at how the effect of mold material plays a role on the microstructure. So of the three images, these are all 400 series aluminum castings, so a 443. And in A, it's a sand cast, B is a permanent mold cast, and then C is a die cast. Now, for this particular, your cooling rates from left to right are increasing. So your cooling rates are increasing, which means it's cooling off faster. Okay, so this is the slowest sand cast, and this is the fastest, and that's your die cast. Okay, typically your permanent molds and die cast are made out of metal, and there are ways to improve or increase cooling rates by adding a flow, a coolant, anything to really absorb and pull out the heat. With a sand cast, it's more difficult to do because you're casting in sand. So typically your casts in sand occur slowly. Now, how does that make an effect on mechanical properties? Well, as stated, this is all the same material, and when you look at the mechanical properties provided, a sand cast has an ultimate tensile strength of 19 KSI. Okay. When you look at a permanent mold cast, because you cooled it a little bit more quickly, it has gone up 4 more KSI, and on the last one, you're looking at another 10 KSI more. So just by changing its cooling rate, you've improved your mechanical properties. So the realm of aluminum. So looking at this first column, aluminum is going to be your first step. Right? So there's your pure form, aluminum. It can be alloyed with zinc, magnesium, copper, manganese, and silicon. After that, it can be alloyed with other materials. So in this first case, you see that you have aluminum and copper, aluminum, copper, magnesium, aluminum, magnesium, silicon, aluminum, zinc, magnesium, and the last one, aluminum, zinc, magnesium, and copper. Those are all your age hardening alloys, which means those are the ones that you are able to precipitation harden through heat treatment. And all of the material, all of the elements, particularly zinc and copper, they form secondary phase intermetallics that precipitate out, hence giving you strength. When you're looking at your casting alloys, that's just purely aluminum and silicon, aluminum, silicon, and copper. I should have changed my color on that. So I'll do blue. Okay, so aluminum, silicon, and copper. Silicon helps a lot with the casting process, as it does with ferrous alloys. It helps with the fluidity of the cast. And then your last column are your work hardening alloys. So this is aluminum, magnesium, and aluminum and manganese. Really make up your work hardened alloys. Those are your alloys that you will strain, harden, cold work in order to improve the mechanical properties you're looking for. So these are the materials that you will not gain strength from a heat treatment. So what are your alloying elements? Well, you have copper, which improves your strength and hardness, and it's typically, you need about 4 to 6 weight percent in order for it to respond to a heat treatment. Magnesium increases strength and hardness as well in silicon alloys, so it's added to silicon, and typically about 7 weight percent in order for it to be considered a heat treatable alloy. Silicon improves casting characteristics, as mentioned, fluidity, improves your wear resistance, and it can be added up to about 25 weight percent. Zinc also increases your heat treat response, and it's typically added with elements like copper and magnesium. So kind of going back, look at that, copper, zinc, magnesium. Here's magnesium, copper, and magnesium. Those are all your age-hardened alloys. And that's why you look and see copper, magnesium, and zinc all have heat treatment responses. So let's talk about the cast alloy designations. So if you're looking at a 100 series aluminum casting, it's unalloyed, and hence it would have the highest conductivity, whether it's thermal or electrical. Of course, the more impurities you add into a pure metal, your conductivity drops. So that's why an unalloyed 100 series would have the highest conductivity out of all the rest of the cast designations you'll see. A 200 series is aluminum and copper. Once again, copper has to be 4 to 5 weight percent. It's a single phase, and it's got good strength and ductility. So it's a single phase, meaning alpha, and you'll have precipitates within that to strengthen the material. 300 series is aluminum, copper, and silicon. Remember, silicon is pretty much added for wear resistance and or fluidity of the casting. Copper, once again, is going to be for heat treatment purposes. The most widely used, you're looking at 356, a 357, 380, 383. Those are typical widely used aluminum alloy casting designations. This material does have a low thermal coefficient of thermal expansion. Looking at a 400 series, it's got good corrosion resistance, castability. Once again, this is just an aluminum plus silicon content. You can modify it by adding magnesium in order to make a 400 series heat treatable. 500 series is aluminum and magnesium. Once again, single phase alloy, corrosion resistant, high strength and toughness. It's good for weldability and machinability purposes. Then you have your 700 series aluminum alloy. This is the one that has the zinc addition to it. It naturally ages, so you're able to get your precipitation hardened secondary phase particles for strength in 20 to 30 days. Good tensile, good brazing properties. And your last one is an aluminum tin. Your 800 series is typically a bearing alloy. Aluminum and tin, this is a bronze alloy, so this is a tin bronze. And it's used a lot in bearings. Fine dendritic spacings are required, and that's for strength purposes. So going to the phase diagram, looking at what you see on the screen, there are a variety of aluminum phase diagrams. Just looking at one particular element here, silicon, you can have an aluminum copper phase diagram, an aluminum magnesium, an aluminum manganese phase diagram, and they're all going to be different. Okay, some of them become even more complicated than what you see here on the screen, but at least up to 20 weight% silicon, you can see that, well, let me zoom in here real quick. This is actually what the phase diagram looks like right here. So all the way up to 100 weight% silicon. You see the melting temperature of aluminum is all the way down here at 660, but silicon is up here at 1430. So just like a portion of the iron-iron carbide phase diagram, this is a binary eutectic phase diagram. Here's your eutectic transformation, where you go from liquid to two phases, alpha plus silicon. Okay, so that's a solid solution of alpha. So when we're looking at some of these, let me see if I'm zooming in enough here. Not really. Can't really read it too well. But each of these different phases provide you with different eutectic silicon morphologies, depending on, for one, your basically it's based on your weight percentage. So if you're looking at a 5 weight%, this is how your cast structure would look. You would have your alpha in the white, that's your solid solution, and then the dark regions around it, giving it that interdendritic morphology. That would be your eutectic silicon. Okay. As you increase, your silicon morphology tends to also change. Here it's interdendritic. In this one here, it's more acicular and needle-like. Now it's becoming thick and blocky. And that is how your silicon content changes as you alloy it with the alloy it into aluminum. Some of the different morphologies that you can come across, these are all done in the as polished condition. And that's one of the nice things about aluminum castings. You can really identify, at least you can see microconstituents in the as polished condition, as long as your technique was good. So these are all at 500x magnification, and it gives you kind of you can get an idea of the coloration. So silicon is black. This is beta aluminum magnesium. That's an intermetallic. You have an aluminum copper iron manganese morphology, so that looks a little script-like. Aluminum copper nickel. These are all different morphologies, and they're all going to be different intermetallics. Let's see any other on here that look. Here's a calcium So if you're using calcium to modify your structure, then it will react with silicon and it'll give you these pentagon-looking shaped microconstituents. And you can kind of gauge a little bit based on the color in the images. These are all 50 Shades of Grey. And I'm not talking about the movie. I'm talking about the constituents on the screen. These all have varying contrasts of gray. And that maxed out with the morphology, it'll help you identify some of the constituents that you see in your microstructures. But if I do etch, what does it do? Well, these are all the different types of etchants you can use for metallography on aluminum. And it'll give you kind of an effect of how it will, how the microconstituent will be affected by it. So typically, hydrofluoric is used in a lot of the etchants. I normally use anywhere between 0.5 to 1 weight percent aqueous solution of hydrofluoric. So in this case here, if you're dealing with silicon constituents, those are outlined, they're not going to be attacked, and the color is light. But magnesium silicate would be colored bright blue. Copper aluminum, it's outlined, it's a little pink. The constituent is light and clear. Oh, it used to be pink, but now it's going to be light and clear. So this is what happens to each of these. So depending on your reagent that you use, this last one over here on the end is known as Keller's. This is one of the most common, excuse me, common etchants to use for aluminum. Cast aluminum is much easier to etch than wrought aluminum. So if I use a hydrofluoric and I'm looking for an iron aluminum intermetallic, the hydrofluoric is going to slightly darken it and it's going to look like it's got brown stains. Okay. Whereas if I use Keller's reagent, it looks outlined, it's going to be uncolored, and it's going to be slightly attacked. So in reality, it's going to matter what you are looking at, or what are you looking for when dealing with aluminum products. So this is where looking at your samples in the as polished condition comes in handy, because you can identify these features prior to etching, and then you pick your etchant and then see if you're see if you get those results. Wrought alloys, generally there are fewer and less alloying elements involved in wrought alloys. Elements have greater solubility. Second phase particles are broken up only by cold working. We dealt with that with ferrous alloys and some of the alloy carbides. They do not go back into solution, so the only way to break them up is by work hardening, cold working. Intermetallics can no longer be identified by external shape. So casting, it was really easy because that's how it's solidified. It's solidified in the shape that we looked at in those previous slides. Wrought alloys are identified by a 4-digit number. Castings are identified by a 3-digit number. So wrought alloy designations, they kind of fall similar. So a 1000 series is an unalloyed aluminum product. Good corrosion resistance, high thermal and electrical conductivity, no problem. Your 2000 series, aluminum and copper, or it has the aluminum copper with the addition of magnesium, because the addition of magnesium helps with the heat treatment, giving a 2000 series comparable strength to that of a low carbon steel. So here's where the strength to weight ratio really comes into play. It does have poor corrosion resistance. Here's your 3000 series. It's just aluminum and manganese, or aluminum and magnesium. This is a non-heat treatable alloy. So this is only a work hardened alloy. Your 4000 series is also not heat treatable. Instead, it has a low melting point, and it's typically used in welding wire and for brazing applications. 5000 series, it's work hardenable. So once again, this is not an alloy that you would be able to precipitation harden. 6000 series, it is heat treatable to a moderate strength. It's got good weldability, good formability, excellent machinability, good corrosion resistance. So you add this bag of goodies and top it off with it being lightweight, and this is one of the most common used series of aluminum, a 6061. Last, you have your 7000 series, which is a heat treatable, and these can be used to very high strengths. So all this talk about elements and alloy designations and such, what do these look like under the microscope? Well, for wrought alloys, these are typically a little harder to etch. So a lot of the times you have to resort to using either electrolytic etches and tint, or heat sensitive etches, color etches, and looking at those under polarized light. Now, this is a 6061 in the as fabricated condition. So that's what that F stands for down here at the bottom of the screen. This is an aluminum 6061 F, as fabricated at 100x magnification. A Barker's electrolytic etch was used, and then it was a heat tint etch was put on the surface and then looked at under polarized light. All the different streaks you see from this point, use the red line. That's my drawing of a straight red line. So everything over on this side, this is the as fabricated condition. You can see that the grains, use that linearity this way, that's how deformed those grains are. So is this fabricated in the cold work condition? Was this hot work? Is this a casting? And the answer to that, because of the severity of the deformation you see in this region, that's going to be a result of this material being cold worked, cold formed, somehow well below the absolute melting temperature of this material. 0.4 weight, 0.4 of the absolute melting temperature of the material. So what's happening over on this end? Well, after this material was rolled, then it gets stamped, and that is what the shear has done on the end of the sample. You can see that it is even more heavily deformed versus the as fabricated side over on this end. And that's because that is the last end of it that got sheared off. Okay, well, what about a casting? Well, this is what the casts look like. This is a cast aluminum 380, and this is at 500x magnification, and it was etched with 1% hydrofluoric. So what can I tell you about this? Well, looking at the microstructure, you can see these little regions all the white, I guess you can say cauliflower looking regions, that is all your alpha solid solution. Alpha solid solution. Okay. All the dark regions in between, that is your eutectic silicon. Okay. Now looking at this, what does this tell you? Is, well, if you're looking at the morphology, is this a fast or is this a slow cooling rate? You can see right on the edge, oops. You can see over here right on the edge, this is the edge of the sample. So this is the surface that I'm drawing with this orange line, okay, to the left of the screen. That is the surface of the material. This is a casting. So at the surface, would you expect faster or slower cooling rates? Since it's at the surface, your cooling rates should be faster. Okay. For this particular material here, it has some intermetallic funny guys, as you can see. Those are your copper Al2 intermetallics. They can also be sludge. If you have a little bit of iron, iron also forms this morphology as well. Well, let's look at this material. This is a modified cast aluminum 333, which is a 300 series aluminum casting. And it was modified with the addition of magnesium. Now, this was actually a failure project that I worked on from the refinery. So looking at its microstructure in this top left corner, that's in the as polished condition. I have not etched either of these images, and they're both at 500x magnification. Okay, so looking up here, you can see the varying shades of gray. Oops, I didn't want to do that. I don't want to do that either. Okay, so here we are. You can see you have this form. You have these slightly darker forms. Then you have these acicular phases. Okay, the acicular phases are your eutectic silicon. These regions in between that have a slightly darker appearance are your magnesium zinc 3. And these regions that are not acicular are copper aluminum. And what's really nice about these aluminum components, you can always put them in the SEM and you can run an EDS map and it'll allocate anything that's aluminum when you would have your high peaks of aluminum, copper, and that's also another way that you can help identify what microstructures you're looking at. Why did this fail? Well, it came across they allowed it to come in contact with hydrochloric acid, at least a cleaning solution that has up to 9% hydrochloric. And what they did is they shut this valve off and they allowed it to sit while they went to lunch. And when they went to lunch, they came back and it exploded. So this whole pump ended up blowing up on them when they went to lunch. The hydrogen is eating away at the aluminum alpha solid solution phase. So you're getting that preferential attack of that aluminum matrix. So looking at this is your aluminum matrix, all the white. Okay, so if you're transitioning and you look at this, it's all attacking anywhere there is aluminum. It is not affecting any you can come through all of this region that used to be aluminum, and you can see where all of the intermetallics, they're still intact. And that's just because the reaction, it's a single reaction between aluminum and the hydrochloric that swaps. So you end up with an aluminum chloride and then hydrogen gas. And the hydrogen gas built up enough pressure that actually blew up this pump. So I thought that was a very interesting project. Looking at another set of images, here's an aluminum die cast. And what I'm illustrating on here, these are both at 1000x magnification in the as polished condition again. You can see that the outer surface is going to be your this image here, because you can see the surface on the right of that image. And this top image over to the left, that's the core of the metal. That's the center of the piece. And you can see that you have two very different microstructures. It's the same material, just in two different locations. So what happens, this kind of goes back into talking about the rate of cooling. This image on the bottom right is at the surface, so you have a faster cooling rate, trapping and giving you the morphology of the eutectic, looking kind of fibrous, and it's interdendritic, and that's what's kind of tracing around all of your alpha solid solution. When you look up at this image at the top left, it's had some time to cool down because the cooling rates aren't so fast. And now you've developed, you know, your eutectic is interdendritic. You still have interdendritic eutectics, silicon. And you also have acicular phase interdendritics as well. This is a 400 series die cast. So if we were to go back up and look at the alloy designation for a 400 series, you can see here. Oh, why is it all highlighted? You can see here that it's just aluminum and silicon. So you're not expecting any additional secondary particles or intermetallics unless the chemistry wasn't correct. Why is all my stuff out? Okay, so those are just some examples of aluminum, what it looks like under the microscope. You can see this stuff in the as polished condition. I love working more with aluminum castings than I do with the wrought aluminum alloys, just for the sake of being able to identify the constituents. They have a specific morphology, and they also have contrast, color difference. These are black and white. If I would have done them in color, you might have seen some pink tints to some of the microconstituents if I had the right alloy, and they don't change until you etch. So it's always important to take a look at these in the as polished condition. So for the assignment, please review in that document labeled terms and definitions. That's going to be until the end of the semester. Turn in your weekly summary talking about aluminum alloys. And I will be posting a quiz that'll be due. I'm going to change this. It's not going to be due Sunday. It's going to be due Monday, April 5th. Okay, Monday, April 5th. So everybody enjoy your Easter holidays, your spring study day on Friday. And I look forward to seeing everybody the following Friday. Remember, our exam 2 will start at 1 o'clock, and we will then have our exam 3 2 weeks from that to catch up. So exam 2 will be next Friday. Good luck. If you guys have any questions, please feel free to shoot me an email and I can address that. I will also be available on Thursday afternoon at about 4 o'clock in this lab as well. Blackboard Collaborate. Have a great day. We'll talk to you guys later. Bye-bye.